on Mozilla.
I'm Shane Stevens and I work for Google on Chrome.
So we had the inaugural Browser Miniconf last year, and what we said is that we wanted to try and have a venue for people hacking on open source browser engines in the area to give some talks about development work they've been doing or other standards, web standards related work that they're involved in. And it was reasonably successful last year, I think, so here we are again. So we have the schedule up here on this website, which is linked to from the actual LCA schedule page. There's some more detailed abstracts about what the talks are if you care to select which talks you're going to attend.
Yep. In the session after lunch for about 40 minutes we have a panel. We did this last year and it was kind of fun. The best part about it was that we ended up sort of moving into some very specific topics and generating some really good discussion on those topics. So we're going to try and seed the panel with topics up front this year. Here are some potential topic ideas that Cameron and I came up with last night. If you have any other topic ideas, feel free to come down and add them at any time during the morning. And then after lunch, we'll come back in here, we'll set up the panel, and we'll give the audience an opportunity to vote on which topic idea they want to discuss. We'll discuss it for about 10 minutes, see where it goes, and then pick another one, and just keep going like that. Do you want to go through the ideas? We probably don't need to.
No, well, we maybe at the start of the panel session we can just list them off and then see which one would start off with. Yeah. All right. So I think that's all the administrative details. So the first speaker, is Guan Yun Huang, and he's from a company in Seoul, I think Seoul.
Yes.
Working on a WebKit port for consumer devices. So thank you, Guan.
Thank you. Good morning. Good morning. I'm Gwang Yun Hwang from Company 100. Our team is working for faster WebKit engine, especially for embedded devices, such as smart TV or smartphones, etc. Such as we are focusing on utilizing the GPU powers and multi-core CPUs in embedded systems. Today, I'll talk about the threaded accelerated compositing in WebKit GTK. Okay, it looks good. Before I explain about the threaded accelerated compositing, I think I needed to talk about what is accelerated compositing. Over the past 2 years, hardware accelerated compositing has been a hot issue. So almost all web engines are implemented this feature. So let's see this example. Yeah, this example. It shows how to composite each layers in accelerated compositing case. There are content layers and div layers and background layer, and GPU can composite these layers onto screen. So this technique is called accelerated compositing. In more detail, we can get the DOM tree from the given HTML page, and from DOM tree, we need a render layer tree to draw something. By draw something like text or images or divs or all of the elements, and we need the graphics layer tree to accelerate compositing. In accelerated compositing case, the compositor uses the graphics layer tree to composite on the display using OpenGL. In the previous example, the contents layer and live layers are graphics layer. So asset compositing provides a way to accelerate animations, transitions, and 3D transforms using GPU. Graphics layer tree has several properties like opacity or transform matrix, so we can easily use the OpenGL to composite these layers onto screen. So This same has been done in WebKit GTK. WebKit GTK implemented accelerated compositing using texture mapper, which is a really lightweight scene graph implementation tuned specifically for the WebKit rendering. From graphics layer 3, it makes the texture mapper layer 3 and renders the scene graph on the screen using OpenGL directly. If you want a detailed description or explanation, I suggest you look at the Chromium documents, or you can also ask Noam Rosenthal, who made the texture mapper. So, though there has been the accelerated compositing, so we have improvement the speed, rendering speed on by implementing accelerated compositing, but it was not enough because the main thread of the web core is too busy to perform compositing. Especially in embedded case, it has a very limited CPU and GPU power, so it was not really insufficient. So the main thread has to execute layouting, scripting, DOM, networking, so there are no time to composite, especially in embedded case. Thus, we running the compositing on the main thread several limits the responsiveness and rendering speed. Here, of the main thread, compositing appears. Of the main thread, compositing means perform compositing on the, where is it? Compositing on of the main thread. So therefore, we can utilize multi-core, and by having separate thread, we can bring a significant performance improvement, especially for the animations, such case animations, and zoom and scrolling. It also improves responsiveness of the user events, like touch events. So this is our overall architecture. Since main thread is doing too much work, we separate the compositor thread, and bitmaps and CSS animations and properties are passed to compositor thread. And compositor thread can play the CSS animations on its own, so there is no interrupt to main thread to run CSS animations. And in case of the touch event or scrolling events, zoom events, compositor thread can render that scrolling using its own scene graph in advance, and then main thread updates the proper viewport. So our requirement is like this. First, responsiveness. We want a fast response at all time. There is a user interaction. There are several user interactions in this area. First is the scrolling or zoom or click the link, etc. And then other user UI events like back button or go button or address button. So we want a fast response at all time. And stability. Especially in the WebKit 2 case, we do not want UI process to crash. We should avoid the UI process crash case. And memory usage, especially in the embedded systems, there are so limited GPU memories, so we have to conserve it. And maintainability. Yeah. We should share code as much as possible with other ports so we can maintain it together and improve it together. So there were several approaches already implemented for the main thread compositing. Implementation of the main thread compositing in macOS Safari, but unfortunately it supports only macOS or iOS. So it is not our option. And Chromium compositor thread used by the Google Chromium. It runs compositing thread of the main thread of the rendering process. In Chromium, they call the rendering process is the same as in WebKit's web process. So It was developed in the WebKit trunk, but it was separated to libcc, Chromium Compositor, and it is really tightly coupled with the Chromium Foundation, so we cannot use this. So it is not our option either. And coordinate graphic system, which is used by the and EFL. It runs accelerated compositing in the UI process, and it uses texture mapper, so we can think about that. So let's look at the coordinate graphic system in detail. Coordinate graphic system is implemented to use texture mapper of the main thread. It was first created by the Noam Rosenthal, who made the texture mapper, and it is improved by the EFL and QTbox. In GTK, we was only needed one single texture mapper layer because we composite we accept compositing, we run accept compositing on the main thread. So, but in coordinate graphics, they need to separate another graphics layer tree to duplicate the layer in the other process or other thread. So they made the coordinate graphics layer tree. Coordinate graphics is only used in the WebKit 2. So web process is where the actually web core runs on, and they produce graphics layer tree by parsing their HTML pages, and then it passes the information about the graphics layer tree, and UI process creates the graphics almost the same from the given past information. And each layer has a separate tiled, split into tiles, so it does not what's that? So coordinate graphics uses tiled backing store, and it split the whole layers into tiles, so it has memory efficiency because it does not render, it does not create bitmap outside of the viewport. So good things is the memory uses. Yes, it uses tiled backing store, so it reduces the memory uses and maintainability. Yeah, we can EFL and Qt shares the same code. So also current GTK uses yeah.
Are you duplicating the image stacking store on both sides of the IPC link, or is it the two tiled storage, is those shared in the GPU, or are they actually duplicating the image storage on both sides of the link?
Yeah.
On there, you have the tiled backing store on both sides. Are those the same backing store, or is that actually separate backing stores?
Yeah. Okay. The question is as I understand, is the tiled backing store is duplicated or a single one, right?
Is the tiled backing store the same as the coordinated backing store?
Yeah. The actual tiled backing store is used in the web core, and it duplicates this bitmap using shared bitmap technique. It duplicates the bitmap on the shared memory on core IPC, and it creates the other backing store. So you have two sets of the tiles. So it uses the double memory. Yes. But it also destructed redundant tiles, so it uses almost efficient. But because of we need the core RP, we need to interaction with the process, so we have to duplicate the tiles in coordinate system.
Seems like you could use the shared memory to share the common tiles.
Yes, but in the case of just for sharing single memory, it is really hard because in the macOS they can lock the graphic surface, but there is no similar mechanism in the X11, so yes, that's a problem. And yes, restrictions, yes. first of all, it supports only WebKit 2. And the moving expensive work from web process to UI process, it lessens the original benefit of the WebKit 2 design, keeping the UI process responsive at all time. And third is it is weak at GPU bugs, especially on the mobile GPU. There are many bugs. GPU drivers are in mobile is really unstable. There are many hard to fix bugs in this area. So when compositing on the UI process, UI process have to use the GPU to draw the actual things, and especially for CSS shaders, we cannot know the author uses what shaders they use it, what shaders they are used in the web page content. So we do not have a safe way to verify this. So the UI process can crash it for GPUs. So we do not want this. And so our implementation, we have implemented another of the main thread compositing, threaded compositor, which is a threaded variant of coordinate graphic system. Threaded compositor compensates the restriction of the coordinate graphics, and as well as benefits from the original coordinate graphics advantages. It separates thread in the web core, so it can support both WebKit 1 and 2. And also, we can keep UI processes simple. And as coordinate compositing is done in the web core. Only web process use the GPU directly. So UI process is isolated from the GPU bugs. So we can provide a graceful crash method on this case. And lastly, we can benefit all the good things from the coordinate graphic system I mentioned previously. The main difference between the coordinate graphics and our compositing thread is the coordinate graphics performs compositing on the UI process, but compositing thread is runs on the web process, and it makes a separate thread for this job. So instead of the IPC, we use the message queue, and we can share the bitmap, tiled bitmap as you mentioned, that problem. And WebKit 1 and WebKit 2 will share the same code path, almost all of the code path, so it is really easier to maintain it. So our approach is to create threaded model in coordinate graphics. So main thread creates the operations, and it passed by the IPC or threaded, and compositing thread will execute this operation. For example, if there are create layer operations, main thread, whenever main thread creates the graphics layer, it create layer operations and with its data, and it passes to web process. Compositing thread, and compositing thread makes duplicated layer. But it looks very simple task, but it was not simple in our case because of that there are so many paths, so many codes are complex in coordinate graphics because it have a little bit history. So we should not break the other ports code. So we need to use refactoring of this design. So let's see the demo. Okay. Okay, this is the little bit shoes. Yeah, this is the WebKit. I built it last weekend, and this is the famous exact compositing demo in WebKit. It is filing leaves. So original version of this web page creates only 30 leaves, but we have to compare the performance about that, so we made 500. So it looks very smooth, but it shows almost 30 FPS. So, but this is our proof of concept implementations on last November. So it is a little bit old, but it works. Maybe you cannot notice the in performance visually, as it is still fast, but it shows almost, yes, 90, because I turn off the VSync, so it almost, I cannot remember what was the performance previous things. Yes, almost 20, almost, what? Yes, 2 times faster, I think. So it is really fast for compositing, to have compositing thread in WebKit GTK. Let's see. Yeah. So this is our data measure in desktop. Since it is a proof of concept, it is a little unstable and it does not match the current code of the WebKit trunk. But you can see the performance difference between the original WebKit GTK and our implementation, especially when the number of the layers increases. WebKit GTK decreases hugely, but it is the same in our case. So we are now contributing thread compositor to WebKit. This is our design document, and this is our metabog for this job. And we are actually, our current job is hugely refactoring the code paths, several code paths related to excellent compositing and texture mappers things. So after that, we are going to contribute actual run loop for the compositing on maybe the end of maybe next month. So I think I should say thank you for listening, and I hope you enjoy the rest of this conference. So.
Thank you very much. Any questions?
So I was wondering, the rendering cost that you moved to the other thread, how much of that was costs within WebKit versus costs within the OpenGL driver? Sort of balance those in the profile.
Excuse me?
So you optimized this by moving a bunch of your rendering
Yes.
activity into separate threads.
Yes.
How much of that time spent in the CPU that was limiting you is time spent inside of WebKit versus time spent inside of OpenGL?
So actually the compositing spans almost 10 milliseconds on the ARM CPU, 10 milliseconds on the single render scene graph, to render scene graph on 10 milliseconds, and we have a time space on 16 milliseconds to achieve the 60 FPS. But in WebKit that uses almost, it's very different because it fires so many timers like scripting, JavaScript to execute, so it is valid for test cases. But in the, HTML games cases, it spans almost JavaScript for 5 to 6 milliseconds at each frame, so it is really hard to match on the 60 FPS on the mobile devices.
So the question is, did you profile the system to find out how much CPU time was being consumed in the OpenGL library itself, contrasted with the rest of the WebKit application? So the question is, if we split the rendering inside the OpenGL library so that the GL library does most of its work in a separate thread, would that solve this problem in the GL library instead of in your application?
Ah, I understand. Actually, we did not profile the actual driver spaces.
Okay.
Yes, but because we do not have an NDA with the.
But you should be able to profile and find out how much CPU time is being used how much CPU time is being used below the driver, and just ignoring what the driver is doing, and find out how much time is being used in your application compared with the driver. Because we're working on some stuff in the Intel drivers right now to split a bunch of the work under the GL API, and we're wondering how much of that is going to help systems like this automatically solve this problem, solve some of this problem, and how much of the additional work you're pushing into the separate thread we're not going to be able to solve below the GL API.
Ah, okay. In the Chromium case, they split the GPU process to actually run the GPU on the other process. So it seems it's a really similar approach to OpenGL driver to Chromium approach, right?
Right.
Yes.
Well, that's a separate process, not a separate thread. That's the,
yeah. We didn't actually profile that things. We think about that option, but in other case, we have another case about that because we made the Canvas GL. We made it 1 year ago. We made the Canvas GL, which accelerates 2D vector graphics on HTML5 Canvas. But we first tried to use the GPU processor on the Chromium, from the Chromium, but we noticed that the little thing will be how we batch the OpenGL drawing code is the most bottleneck the whole code. So we needed to batch the whole GL code. So we needed to gathering the Canvas drawing code, and we made the automatically batch systems. So it reduced the times that the separate OpenGL codes. And in the threaded compositor case, I think it is matter on how we optimize the scene graph to render on the screen. It is much big factor, I think. So I said about the texture mapper because texture mapper uses actually in this layer. So in other cases, Qt folks used Q scene graph or Q graphics view. They use that, but it has so many abstraction layers, so they could not optimize the whole scene graph to render this. So they made a direct scene layer to use OpenGL. That's the texture mapper. So it is, I think that is the bottleneck of that problem.
All right, so we might have to leave it there. Thank you again, Guan Yin.
Thank you.